So some of you may have seen a recent report from the Wi-Fi Alliance. They did a survey, and according to their results, 8 out of 10 people would rather ditch their iPod than give up their Wi-Fi network. When they surveyed the same group, asked them whether to trade between their home phone and their wireless network, again, 79% would rather give up their phone than their wireless network. So surveys and statistics, you can kind of draw your own conclusions, but I think it's safe to claim that people are really attached to wireless networks. So why is that? I think the simple answer is simple connectivity and easy connectivity. Connectivity is compelling, and whether your personal addiction is email, IM, online gaming, or MySpace, you need to be connected. And also because it's compelling, people are willing to take risks to get connected, to get online. Sure, it's an open, unsecured network, but I'm going to connect anyhow. So in this room, we see people on the wireless network. You even see people at DEF CON on the wireless network, even though the risk there is, say, 1,000 times higher than would it be in a normal coffee shop. So we may be feeling okay in taking that choice, making that decision between risk and benefit, but do you feel equally sure that the people you advise or the users you manage, when they go out and make that same decision? We need to make sure that the connectivity choice today doesn't come back and bite them a week or a month down the line. We need secure networks that are easy to set up, but we also need to make sure that when users move out of that secured environment, they're also protected as much as we can. Today we're going to give you a short look at the Vista stack. We're going to look at into the components, look at some of the changes we've made, but we're primarily going to focus on the extension points, the pieces we've added that allow you to build on and extend the stack and build security tools on top of what we've already done. So we're just going to give a brief introduction, just some small piece of background. We'll take a look at the various software components in the stack, and we'll look at the behaviors, how that software stack interacts with the user and how it interacts with other wireless devices. And we'll have time for question and answer at the end. This isn't quite the same as was published in the conference CD. We just had too much material in that presentation, more than we can get through, and we actually want to do some demos rather than just flip through slides. So we're actually going to show you some tools built on top of the stack. And the tools are changing up to about an hour ago, so hopefully they're going to work. So it's pretty obvious to everyone why you'd attack wireless. You find wireless networks everywhere, you're going to find someone using it, so there's a possible victim. I've classified wireless attacks into kind of two buckets. The first one is protocol attacks. Here we're looking at either a vulnerability in the specification itself or just how vendors implemented that protocol. And behavioral attacks are looking at the kind of next layer up, how the actual logic on the device works, how it does things like its auto-connect logic, how it does network discovery. So with two classes of attacks, we have kind of two approaches we've taken. For protocol exploits, well, the protocols in Wi-Fi 802.11 are all standards-based. So we need to make sure that the standards bodies are evolving these in a secure manner. And we try to be active in both the IEEE and the Wi-Fi Alliance. We're trying to choose secure defaults. So whenever the stack is making a decision on behalf of the user, we're going to try to do it securely. So if we see a network that advertises WPA2 and WEP, our discovery engine is always going to try WPA2 first. And then we're just going to try and whatever best practice we have in design, coding, and testing, we're going to try and apply that to our body of code. And make sure that all the protocol passes we have are as solid as we can get them. Behavioral attacks is all about the upper layer implementation. So here we're looking at known attacks. So if there's a paper or a report issued, we want to take a look at it, see what we can learn, and see how we can address it in our code. What I mean by promoting secure defaults is whenever we give a user a choice, we're going to make sure that the most secure option is the first one. If there's a set of dialogues where they can say click through, just by hitting XXX, or where they can cancel out of, we want to make sure they end up in a secure state at the end of that. What we're really trying to avoid here is any opportunity for them to become insecure through inattention. It sounds really obvious, but there's a lot of software out there that doesn't do that. If they do decide to make an insecure choice, we want to try and inform them of that risk and what potential impact there is. And we want better manageability so that if you're responsible for the set of client machines, you've got some control over, you can constrain what kind of networks they can attach to, where they can go. So why would we want to rewrite the wireless stack? Mostly it's down to feedback. We hear requests for features from customers, from OEMs and partners. We've had feedback from the community itself. We've had the rogue attacks from K2 and Dino. Simple Nomad did some stuff on ad hoc. So we try to take all that into account and bring it into what we've done. In fact, this whole talk is based on we had a whiteboard chat with Beetle one day, and this kind of talk evolved from there. If some of you may have seen the earlier talks on process changes and new tools, so we try to make sure we apply all those to the new software stack. And then the standard bodies are marching along on their own. There's a whole alphabet soup of 802.11 protocols. There's N, K, D, it goes on. So we need to make sure we roll some of those back in. And we also want to make sure that the platform is extensible so that as new protocols and new features come along, they can be brought back into the stack without having to do minor changes, with minor changes, not having to do a complete revision. So our goals are pretty simple for Vista. Obviously, we want to make it as secure as we can. We want to make it more manageable. We want to make it extensible. So there's APIs, information being rippled out, so you can look deeper into the stack than you could before. And again, transparent, so a lot of the information that was kind of locked down in drives before, it's available to system services, it's available to applications. So now we're going to take a quick look at the architecture. We're going to look at XP first off to kind of set a baseline, and then we'll talk in more detail about what Vista does. So this is the basic architecture for XP. There are 3 layers. There's drivers at the bottom running in kernel. There's a service layer running above it. And then there's a user application, a user interface on top. So a kernel mode driver. In XP, the driver basically implements the entire .11 stack. Both the Mac and the Phi are all done in the driver. It's an emulated Ethernet driver. By that, I mean it plugs into the rest of the stack as an Ethernet device. So part of what the driver does is also it's translating the frames between 802.3 and 802.11 as it passes them up and down to the stack. So that basically the driver is implementing all of the standard Ethernet OIDs. It appears to the rest of the system just like an Ethernet driver, except that the driver also implements a handful of additional wireless-specific OIDs. So OIDs are object IDs. These are effectively buffers that get passed up and down between the driver. So you can think of these as the application interface to a driver. So the set of wireless OIDs are responsible for things like scanning, connect, disconnect. Above the driver, we have our wireless zero config service. So this is the guy that's actually driving those OIDs. It's talking down the driver, and it's using a special function protocol stack called NDIS-UIO to actually communicate up and down with the driver and push these OIDs up and down. The service is responsible for the auto connect logic. It also is responsible for like manual connection, pushing things like scan results up into the user interface, to going between the service layer where there's always on code running into each of the user contexts. And it also contains the 802.1x supplicant. It has some interactions with DHCP and some limited interaction with group policies, so you can push down some configuration to the service. And finally, on the top, there is the user interface components running in the context of the logged on user and communicating back and forward to the service through LRPC. So the XP design is pretty good for what it's intended for, which is connectivity. There's some things we can do better, and there's some changes that will come along in service packs. But basically, it's intended just for that connectivity. The core problem with the XP design is it's really pretty much a black box. Packets come in, packets go out. You get some kind of user interface notifications. But if you wanted to write an application that sits out on top and drove wireless, you can't really do that unless you wanted to go and reverse engineer the RPC interfaces. It's quite common that enterprises will deploy Cisco equipment, so they might want to use Cisco CTX security. You can't add that into our client. If you want to have that, you've got to rip our client out and put it in a separate software stack. So we really want to kind of get away from that model in Vista and trying to open these pieces up as much as we can. So this is the Vista architecture. It looks pretty similar. Still got those 3 big layers, drivers at the bottom, an expanded service layer, and then some more options at the top in terms of user interface and applications. What we're actually going to do is we're going to drill down a little bit into each of these layers and talk in a bit more depth, and then we'll show you some demos at some of those layers. So the first level is we're going to talk about is the stack. We're going to start from the bottom, work up. We're going to look at the drivers first off. So one of the things you'll notice is we actually have 2 driver models. There's the existing driver model, exactly the same as you saw in XP. So we have that model in there so that older devices will still continue to work. We refer to that as the FAT model. FAT isn't an acronym for anything, it's just that these are large bodies of code typically. But we also have a newer driver model. So on the left-hand side, you'll see that effectively we've broken that driver model into two. At the bottom layer, we still have an IHV, a hardware-specific mini-port driver. This is doing the PHY and the lower MAC functions. But actually now, rather than exposing 802.3, it's actually exposing 802.11 at the top end, and it's binding into a Microsoft driver. So this driver layer is then common across all hardware. This driver layer does the upper MAC functions, and it also does that translation between 802.3 and 802.11, so it can plug into the rest of the stack. And again, all of this stuff is running inside NDISC, which is NDISC is the kind of standard driver interface for network cards. NDISC is responsible for things like driver lifecycle from installation. You can run co-installers as you install a card. It's responsible for the binding, so it's how the stack and the drivers connect together, and how we multiplex packets up and down through the stack. So I mentioned we were going to talk a little bit about some behavior changes as well. So this is one of the first ones. So in XP, any network that's in our preferred list, we actually send out a probe for that. The problem with that is all those probes for every network, every you visited, get exposed on the air, and there's a potential for an attacker to spoof those networks and try and get you to connect. We made some changes for this in Vista. So by default, we don't issue probe requests anymore, unless you've actually got a network that you configure to be non-broadcast, so you try to hide it, in which case we have to send a probe to actually find that. But that's the only case we'll actually send a probe. Another similar change we've made is when you resume out of Hibernate or Standby, we're actually going to take a look on the air first to see if we saw the last access point we're at, rather than just sending out some probes or some traffic for it. And that's just to try and stop us from leaking the last network you connected to. So again, just to try and make the client more passive, release less information than we did previously. So there is one kind of big side effect of this. It's pretty common advice out there to actually hide your home network's SSID to make it non-broadcast. It's always been pretty marginal advice because it doesn't work the moment someone sends traffic, but it's fairly common. But now it's really going to be counterproductive, because if you do that, your client is going to, if you travel around, you move your laptop, your client is actually going to be probing for that network, whereas if you'd made your home network broadcast, you wouldn't actually see that at all. Similar effect we have in SP2 is if we don't see any preferred networks we want to connect to, we try and park the card. And we do that currently by plumbing down a random SSID down to the driver. The problem, again, is because we're probing for everything, that random SSID gets pushed out, and there's potential for an attacker to spoof it. Vista, we've taken two approaches to fix that. The first one, for the new driver model for native Wi-Fi, we actually have a specific OID, a command that goes down to the driver to say, just park, wait till we tell you to do something else. For the older drivers, for the FAT model, we still push down that random SSID, but now we also push down a random key. So although the attacker might see that network, they actually won't be able to get the client to attach. NDISC ports is it's a very geeky kind of developer change, but we like it. In previous versions of the OS, the main piece of connectivity information that rippled up to say you're now connected was a media connect event. That's very much a kind of legacy event from the days when simply plugging into a jack in the wall was sufficient indication that you could flow packets.